Hello, I'm Klemen. The title of our paper is Mir in the Middle, Multi-Scale Upsampling and Matching for Cross-Resolution Face Recognition. This paper is a result of a joint research project between our group at the University of Ljubljana, Slovenia, and our colleagues from the Istanbul Technical University in Turkey. The problem we try to address is specifically the large domain gap we commonly encounter in surveillance scenarios. Namely, we're typically trying to recognize subjects from potentially very poor quality surveillance images by matching them against a closed set of high quality gallery images. If we use the same face template engine, such as a face recognition deep neural network, to extract a face template from both a probe image and a gallery image, we get two different feature vectors. If we observe the distribution of the probe and gallery templates, we can see that they're distributed very differently, which makes matching them directly difficult and results in poor recognition performance. Now, different kinds of solutions to this problem have been proposed. For example, you can train a face recognition model explicitly to be invariant to the quality of the input image. Alternatively, you can either degrade the gallery images or improve the probe images to help bridge the domain gap. Attempts have also been made to find explicit mappings between the distributions of probe and gallery image templates. So our approach assumes that face templates extracted by deep neural networks include at least some information on the identity of the subjects, as well as other factors such as background, pose, lighting, gender, age, and image quality. Of course, we're primarily interested in the information about the identity of the subject. For the problem of face recognition, all the other sources of variability in the face templates basically represent noise to us. And specifically, we're trying to get rid of the information related to the effects of different image quality in the probe and gallery image templates. And we do this by treating a given face template as representing identity information, which is marked as IX, corrupted by noise due to image quality factors, which is marked as epsilon G. So to get rid of the noise, what we do is we generate many different quality versions of the same image. So if the noise is normally distributed, it should average out to 0 as the number of images generated is increased. So to do this with gallery images, we use a stochastic iterative degradation process. We define a few different degradation operations such as blur, noise, and color jitter, and each of them has its own randomly determined parameters. And what we do then is we chain these operations randomly to get a degraded gallery image. The result is a set of many different degraded gallery images with widely varying quality characteristics. And to get a set of quality varied probe images, we use a multi-scale, multi-hypothesis super-resolution model. Our model outputs the input image magnified by factors of 2 times, 8 times, and 4 times, with multiple hypotheses at every scale. So, given the sets of probe and gallery images generated with this process, the final step is to match the sets against each other and generate a score that represents similarity between a single probe image and a single gallery image. And the first option we tried here is to fuse the templates of probe and gallery images separately, so that we have a single probe template and a single gallery template. Here we can combine the templates by either summing them all up or by concatenating them. Then, once we have a single fused gallery template and a single fused probe template, we can combine them by calculating the similarity score between them. And the other option is score fusion. Here we just compute the correlation similarity scores between all possible pairs of probe and gallery templates. Then we can either take their sum or just use the maximum similarity score between all of the generated scores. And it's also possible to use some combination of these two approaches. For example, here we first fuse the gallery templates by summing them all up, and then we compare the fused gallery template against each of the probe image templates. And we use the maximum out of these similarity scores to represent the final similarity between the original probe and gallery image. Now, to evaluate the effectiveness of our proposed method, we used the surveillance cameras phase database. This database consists of 120 different subjects, and each subject has one high-quality gallery image and 5 resolution probe, low-resolution probe images captured by different security cameras. So to extract the face templates, we used unspecialized face template deep neural networks without fine-tuning. Specifically, we used the ArcFace ResNet models trained on the Glint 360K dataset. And as you can see from the results, our method is state-of-the-art, and it even outperforms other methods that were fine-tuned for the SCFace dataset. We can also look at some specific failure cases of our method. So in cases where the probe image is very poor quality and most of the identity information is lost, we can see that the method still matches the probe image against images with similar characteristics, such as haircut or clothing, which are the only attributes that can be reliably determined from the image. That's all. Thank you for your attention, and I'll be happy to take any questions.